Suppose we do an experiment and we get a set of data points being x1, y1, x2, y2 up to xn, yn. And we want to obtain a mathematical relationship being y is a function of x by fitting a curve to these points in the plane. So this can be a line, a quadratic polynomial, and so on. And these data points, for example, may represent the force versus the displacement of a spring. And we want to determine the stiffness of the spring. Now if the data points that we obtained were collinear, so if they all lie on the same line, then the line would pass through all the points, and the unknown coefficients from the equation of a line, being the y-intercept and the slope, would satisfy the following relationships. So for point 1, we'd have a0 plus a1 multiplied by x1, and for the second point, we'd have a0 plus a1 by x2, and so on up to yn is equal to a0 plus a1 by xn. So we can write this in matrix form. So we'd have some matrix multiplied by those constants is equal to the y vector. So in the first equation, we'd have a0 plus a1 by x1 is equal to y1. And for our second equation, we'd have a0 plus a1 x2 is equal to y2, and so on. And finally, a0 plus a1 by xn is equal to yn. So we'd have a by our vector of coefficients is equal to y. So as we can see, if the data points are not collinear, then this system here would be inconsistent, and we can't find the coefficients a0 and a1 that satisfy this equation exactly. And therefore, we'll look for a least squares solution. So we'd have v dash with the approximate coefficients being equal to a0 dash and a1 dash. So therefore, the line with the coefficients a0 dash and a1 dash, where the coefficients come from a least squares solution, is called a regression line. Or a least squares straight line fit to data. So if we can find this linear relationship, then for some point x, we can approximately predict the value y if we had this relationship. So remember, the error in the least squares approximation was the norm of y minus a by v, and therefore the least squares error using these relationships is equal to y1 minus a0 minus a1 x1 squared plus y2 minus a0 minus a1 x2 squared, and so on up to yn. So we'd have yn minus a naught minus a1xn squared. And therefore we can write these terms as e1 squared plus e2 squared and so on up to en squared. So this is the least squares error in our approximation. And let's just copy this graph down here. So geometrically, we see that EI measures the error at the point xi, yi. So for example, the error at this point is our measured y value, which is the exact value, minus this distance over here, which is the value on the regression line. So therefore the least squares line of best fit, or regression line, minimizes this error. And recall that we can obtain a least squares solution of our system AV is equal to y by solving the normal system associated with it. So recall this normal system was the transpose of A multiplied by A multiplied by V is equal to A transpose multiplied by Y. And now we'll do an example to demonstrate this. Let's find a linear relationship between these points that were obtained from an experiment. So recall that the least squares solution of our matrix A by V is equal to Y is obtained by solving the normal system associated with it. So we have A transpose A by V is A transpose by Y. So the linear relationship that we want is Y is A naught dash plus A1 dash by X, where these constants are obtained from a least squares solution. So therefore A has the values 1 in the first column, corresponding to this constant, and in the second column we have the x values 1, 2, 3 and 4. So from this we can get A transpose multiplied by A, and I'll let you do this multiplication, which will give you the following matrix. So recall that this matrix is symmetric, and now we can invert this matrix. So we have the inverse of A transpose A being 1 over the determinant, which is 120 minus 100, and we swap A and D and negate B and C. And I'll let you simplify this. And noting that our y vector is just a vector of y values, so 2.5, 5.2, 6.5 and 8.3. We can solve this equation. So we have the inverse, which would multiply by A transpose by Y to obtain V. And we'll call this V dash because it's the least squares solution. So that would give you 0.95 and 1.87. So that's the equation of our regression line. So we have 0.95 plus 1.87x. So if we plot these points and the regression line, it'll look something like this. So here we can see the error between the exact data points and the values on the regression line. So these 2 points have less error.